Okay, this is lesson 1-1, investigating patterns. Our learning targets are to identify patterns in data, use tables, graphs, and expressions to model situations, and to use expressions to make predictions. So we're going to cover those things in this lesson. We're going to start with reading this paragraph. Meising spent his summer vacation traveling cross country with his family. Their first stop was Yellowstone National Park in Wyoming and Montana. Yellowstone is famous for its geysers, especially one commonly referred to as Old Faithful. A geyser is a spring that erupts intermittently, forcing a fountain of water and steam from a hole in the ground. Old Faithful can have particularly long and fairly predictable eruptions. As a matter of fact, park rangers have observed the geyser over many years and have developed patterns they use to predict the timing of the next eruption. Park rangers have recorded the information in the table below. Number 1 asks us to describe any patterns you see in the table. So, looking at the table, what patterns do we notice? I see here that the length of eruptions are increasing by 1 minute each time. 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4. On the other side of the table, I notice that the approximate time until the next eruption is increasing by 12. 46 plus 12 is 58. 58 plus 12 is 70. 70 plus 12 is 82. So the pattern that I see in the table, the approximate time until the next eruption increases by 12 each time. Number 2, why might it be important for park rangers to be able to predict the timing of Old Faithful's eruptions? So this is a real world scenario. These park rangers may want to know the timing because they want to control the crowd. They want to keep people safe. So crowd control or safety. There may be some other reasons that you may think of. Okay, number 3, if an eruption lasts 8 minutes, about how long must park visitors wait to see the next eruption? So our question is, how long must park visitors wait to see the next eruption? Explain your reasoning using the patterns you identified in the table. Well, if I go back to the table, I see that the length of eruptions, they stop at 4. But my question asks me about an eruption that lasts for 8 minutes. So that means I need to continue the table. So I'm going to go over here to the side. Since my table stopped at 4, I'm going to pick up at 5 and continue to 8. Now remember, the length of eruption times, they're increasing by 1 minute as I did in my table. And then the approximate time until the next eruption is increasing by 12. So the last eruption time that we had was 82 minutes. So for 5, I'm going to do 82 plus 12. Well, that gives us 94. And then I'm going to continue. I'm going to do 94 plus 12, which would give us 106. And then I'm going to continue. 106 plus 12, that would give us 118. And then the last time for our answer, 118 plus 12 is going to give us 130. So how long must the park visitors wait to see the next eruption? The answer to our question, they must wait 130 minutes. Okay, moving on to number 4. Number 4 is asking us to graph the data from the table on the grid. So I'm going to go back and look at my table. Okay, so I have the length of eruption times, which is located on the x-axis. And then also in our table, we have the approximate time until the next eruption, which is located on the y-axis. So these will be our y values, and these will be our x values. What would be easy to do here is to create coordinates or points from the information on the table. So the coordinate or the point for this data would be 146. The coordinate for 258 would be 2, comma 58. The coordinate for 370 would be 370. And the coordinate for 482 would be 4, comma 82. So we're going to plot those points on our graph. So we're plotting 146. I'm going to 1 and up to 46, which would be somewhere about there. I'm going to 2 and up to 58, which would be about there. Going to 3 and up to 70, and going to 4 and up to 82. Notice I'm leaving those points just as they are. I am not connecting them to make a line. Okay, now we're going to move on to number 6. But first, let's read some info here. They're telling us that patterns, the pattern that we just recognized in the table, can be written as a sequence. Well, what is a sequence? A sequence is a list of numbers, and each number is called a term of the sequence. And then they give us some examples of what a sequence looks like there. Okay, so number 6 says using the table or graph above, write the approximate times until the next Old Faithful eruption as a sequence. So let's look at our table, and we want to write the approximate times until the next eruption as a sequence. That means we want to list the numbers out, placing a comma in between each term. So we're going to start off with 46, comma, 58, comma, 70, comma, 82. Now, remember, over here, we continue the table. So just because our table stops right here, doesn't mean that the approximate times don't continue to increase by 12. So what we can do to note that this can continue is put a comma and 3 dots. Number 7. How would you describe this sequence of numbers? I would describe it as the sequence constantly increases by 12. Okay, now we're going to move on to number 8. In the table below, 5 and 8 are consecutive terms. A consecutive just refers to items that follow each other in order. Some sequences have a common difference between consecutive terms. The common difference between the terms in the table below is 3. Well, looking at how these terms are changing, every time they increase by 3. So the common difference is 3. We are going to omit number 8. So we're moving on to number 9. The sequence of next eruption times has a common difference. Identify the common difference. So looking at our sequence, what's our common difference here? Every time we increase by 12. So the common difference is 12. Okay. Moving on to number 10, and in number 10, we are going to do C and D. I am going to give you the expression that represents the number of minutes an eruption lasts. Okay, that expression is 46 plus 12 times n minus 1. So what we want to do is check the accuracy of your expression by evaluating it when n equals 2. Well, let's look at our table. What are we supposed to get when n is 2? When n is 2, or when the length of the eruption is 2, the approximate wait time is 58. So let's see if that checks out using this expression. So I'm going to evaluate the expression 46 plus 12 times n minus 1. I'm evaluating for when n equals 2. So that means I'm going to replace n with 2. 46 plus 12 times 2 minus 1. Now I just need to simplify using my order of operations. So what I would do first here is the parentheses 2 minus 1. So 46 plus 12 times 2 minus 1 would be 1. Okay, next in my order of operations, I'm going to do my multiplication. So 46 plus 12, 12 times 1 is 12. And then lastly, 46 plus 12 gives us 58, which checks out. So our expression is accurate. Now you're going to use the expression to determine the number of minutes a visitor to the park must wait to see another eruption of Old Faithful after a 12-minute eruption. So we want to know after a 12-minute eruption. That means this time we are replacing n with 12. 46 plus 12 times n minus 1. We're evaluating this expression for when n is 12. So I'm going to replace the n with a 12. Notice that doesn't mean I get rid of the other 12. That stays. Now I'm going to follow my order of operations. 12 minus 1, 11. Follow my order of operations. I'm doing this multiplication next. So 12 times 11 gives us 132. And then add those up, and we get 178. So how long the park